On the first night of July 2025, a robotic telescope sitting quietly in the mountains of Chile recorded a single faint smear of light moving across the black. Nobody was watching it happen in real time. No alarms went off, no sirens, just a machine doing its job, scanning the sky the way it does every single night, looking for rocks that might one day hit us. But when the data was reviewed the next morning, something didn't add up. The object in that smear of light was moving at over 200,000 kilometers an hour, and it was not going around our sun. It was going through it, coming from somewhere outside our solar system entirely, on a path that would take it in, past us, and back out into the dark forever. Within 48 hours, astronomers on 3 continents had canceled their existing observation schedules. Within a week, the biggest telescopes on Earth and in orbit around it, Hubble, the James Webb Space Telescope, ground-based observatories in Chile and Hawaii, were all pointed at the same tiny point of light. And by the time the dust settled, quite literally, scientists were left holding a set of numbers that some of them still cannot fully explain. This is the story of 3I/Atlas, only the third confirmed visitor from outside our solar system in the entire history of human astronomy. An object that, according to multiple independent research teams, may have started forming before our sun even existed, before Earth was a ball of molten rock, before there was a solar system here at all. Stay with me for the next half hour, because this story does not give you the strange part right away. It builds, piece by piece, measurement by measurement, until you're standing exactly where the scientists were standing, staring at spectral data from a machine that cost $10 billion to build, and asking a question that sounds almost embarrassing to say out loud. What if this thing isn't just old? What if it's carrying something? Let's start with what space actually is, because most of us picture it wrong. We think of the gap between stars as truly empty, a vacuum with nothing in it at all, but that's not quite right. Scattered through that vast darkness is debris. Leftover material from the violent, chaotic process of building planets. When a young star system is forming, giant planets are still finding their orbits. And in that process, they fling smaller objects around like a slingshot. Comets, asteroids, chunks of frozen gas and rock get thrown clear out of their home system entirely. Once that happens, they don't stop. There's nothing to stop them. They just keep moving, drifting through interstellar space for millions, sometimes billions of years, completely alone, completely dark, completely unseen. In theory, our solar system should get visited by these wandering objects fairly often. In practice, we didn't actually catch one until 2017. That object was called Oumuamua, a Hawaiian word roughly meaning scout or messenger from afar, and it was strange from the very first image. It was elongated, tumbling end over end, and it had no visible tail, no glowing cloud of gas, none of the things you'd expect from a comet, and yet it was accelerating slightly as it left our solar system in a way that gravity alone couldn't account for. Scientists threw out theory after theory. Maybe it was an iceberg made of frozen hydrogen. Maybe it had an unusual fractured shape that let outgassing push it in an odd direction. One Harvard astrophysicist, a man named Avi Loeb, went so far as to suggest it might be artificial, a thin, reflective object, possibly even technology. Most of the scientific community pushed back hard on that idea, but here's the uncomfortable truth. Nobody ever fully explained Oumuamua. It just left, gone. No second look, no follow-up mission, nothing. 2 years later, in 2019, a second interstellar visitor arrived called Borisov. This one behaved exactly like a normal comet is supposed to. It had a glowing coma, a proper tail, all the familiar features. Astronomers studied it, learned what they could, and largely moved on. Less mysterious, less controversial. And then, 6 years after that, came the third one. And this time, everything about it was different. On July 1st, 2025, a survey telescope in Rio Hurtado, Chile, part of a network called ATLAS, the Asteroid Terrestrial Impact Last Alert System, a project literally built to warn us about incoming space rocks, picked up a fast-moving, faint smudge. When astronomers calculated its trajectory, they immediately knew what they were looking at. This object was moving on what's called a hyperbolic path. In plain terms, it was moving too fast for our sun's gravity to ever capture it. It wasn't orbiting us, it was just passing through. And the speed on that trajectory was almost unbelievable. 221,000 kilometers per hour at the moment of discovery, a number that would only increase as the object fell deeper into the sun's gravitational pull. To put that in perspective, that is dramatically faster than either Oumuamua or Borisov ever moved. And here's the part that most people watching the headlines never stop to think about. Speed, for an object like this, isn't just a number. It's a clock. The faster an interstellar traveler is moving when it enters our solar system, the longer, statistically, it has likely been traveling through the galaxy to build up that speed. Astronomers who modeled the comet's trajectory backward concluded that it most likely originated from what's called the thick disk of the Milky Way. a puffier, more scattered region of our galaxy that sits above and below the flatter disk where our own sun lives. Only around 15% of the galaxy's stellar mass is out there. And crucially, most of the stars in that region are old. Not old in the way we usually use the word. Old in a way that's hard to even picture. Older than our sun. Older, potentially, than most of the stars we can see with the naked eye on a clear night. Word of the discovery spread through the astronomy community almost instantly. Observing time on major instruments, time that normally takes months to schedule and is fought over by research teams around the world, was rearranged within days. Everyone understood the stakes. This was a one-shot opportunity. A messenger from a completely different star system sailing through our neighborhood for the first and only time, warming up under our sun's light just enough to release whatever it had been carrying, frozen and sealed for who knows how long. Miss the window and it's gone. Forever. No second chances, no follow-up trip. We don't have anything close to the technology to chase down and catch an object moving at that speed. NASA's Hubble Space Telescope got its first clear image on July 21, 2025, when the object was still nearly 280 million miles from Earth. What Hubble captured was striking, a teardrop-shaped cocoon of dust surrounding a solid, icy core. Early estimates of the nucleus size were incredibly broad, anywhere from under half a kilometer to well over 5 kilometers across, because measuring a solid core through a bright cloud of outgassing material is notoriously difficult. It wasn't until months later, after the comet had already swung past the sun and started heading back out, that scientists were able to separate the glow of the surrounding dust from the solid body underneath. Once they did, they arrived at a more precise number, an effective diameter of roughly 2.6 kilometers. Sit with that for a second. A solid chunk of rock and ice, 2.5 kilometers wide, that has been drifting alone through interstellar space for an almost incomprehensible amount of time, happened to cross paths with our sun, and we caught it, on camera, in real time. Every instrument that could be aimed at it was Hubble, the James Webb Space Telescope, the European Space Agency's JUICE spacecraft, originally built to study Jupiter's moons, NASA's Lucy mission, designed for asteroids near Jupiter, ground-based giants like the Very Large Telescope and ALMA in Chile, and the Subaru Telescope in Hawaii, an entire fleet of some of the most expensive scientific instruments ever built by humanity, all turned toward a single object, racing away from us, that we would never see again. And what they found didn't just satisfy curiosity, it reshaped the entire conversation. Detailed trajectory analysis showed the comet moving at close to 60 kilometers per second, faster than either of the two previous interstellar visitors, suggesting it had been ejected from its home star system with enormous kinetic energy. Something violent happened at the birth of this object, a close gravitational encounter with a massive planet, most likely, flinging it outward with so much force that it has been hurtling through this galaxy at that speed ever since, through the dark, through the cold. For a length of time we are about to get into, and that number is going to change how you think about everything that came before it in this story. The James Webb Space Telescope's near-infrared spectrometer turned its chemical eye on the comet, and the results were almost immediately flagged as extraordinary. Webb detected exceptionally high levels of deuterium, sometimes called heavy hydrogen, a variant of hydrogen with an extra neutron in its nucleus. The amount measured was roughly 30 times higher than what we typically see in comets that formed right here in our own solar system. Let that number actually land. Not 30% higher, 30 times higher. This isn't a small deviation you could explain away with measurement error or a slightly different formation environment nearby. This is a fundamentally different chemical fingerprint, the kind of signature that tells you, unambiguously, that this object did not form anywhere close to where our own comets formed, under anything resembling the same conditions, or anywhere near the same point in time. Based on this deuterium ratio and other isotopic clues, research teams estimated that 3I/Atlas may have formed somewhere between 10 and 12 billion years ago. During a period astronomers sometimes call cosmic noon, an era when star formation across the universe was happening at its most intense and rapid pace. The environment that gave birth to this object was likely a cold, dense molecular cloud, and the sheer abundance of heavy water locked inside its ice tells us it spent its earliest years in a deeply, deeply frozen state, far colder than almost anything we can point to inside our own solar system today. Now compare that number, 10 to 12 billion years, against what we actually know about our own cosmic neighborhood. Our solar system is approximately 4.6 billion years old. Earth itself is about 4.5 billion years old. The very first single-celled organisms on our planet didn't appear until roughly 3.5 billion years ago. When this comet was forming, none of that existed. Not the sun, not the Earth, not even the raw, scattered dust that would eventually clump together to build either of them. Whatever star system gave rise to this object was part of the very early Milky Way, back when our galaxy itself was still young, chaotic, and forming stars at a blistering rate. This wasn't just one team's conclusion either. A peer-reviewed paper published in the journal Nature in June of 2026 laid it all out in detail. And it wasn't a single study. It was two, run independently, using different instruments, arriving at the same extraordinary place. One team, led by a researcher at NASA's Goddard Space Flight Center, worked from James Webb data. A separate team, led by a researcher at the University of Edinburgh, worked from data gathered using the Very Large Telescope in Chile. Two different groups, two different instruments, two completely separate analytical approaches, and they landed on the same conclusion. This comet is ancient in a way nothing we've studied up close has ever been, a literal fragment of the early Milky Way, a physical sample of chemistry from a time before our star ever ignited. One of the lead researchers put it simply. This was a unique opportunity to study an object that likely predates our sun and our solar system entirely. On one hand, it gives us direct insight into a distant place and time we could never otherwise access. On the other hand, it tells us something important about just how unusual or how ordinary our own solar system might actually be. Read that last part again, because it matters more than it sounds like it does on the surface. How unusual our own solar system might be. Because what this comet carried inside it wasn't just old chemistry, it was different chemistry. Chemistry that simply doesn't match the recipe we see anywhere else nearby. Researchers found the composition was distinctly unlike solar system comets in several specific ways. Unusually high carbon dioxide levels, surprisingly low ammonia, an extreme ratio of heavy hydrogen to regular hydrogen, and an elevated ratio between two different forms of carbon. Taken together, these isotopic fingerprints point toward formation in an ultra-cold environment, below 30 degrees on the Kelvin scale, roughly minus 243 degrees Celsius, somewhere around 12 billion years ago. To give you a sense of just how cold that actually is, it's colder than anywhere we can currently point to inside our own solar system. Whatever corner of the galaxy this thing formed in was so dark, so distant from any nearby star's warmth, that the chemistry locked inside it has essentially sat frozen, unchanged for 12 billion years. A perfectly preserved capsule from the early universe, delivered unannounced to our own front door. And then Webb found something else. Something that shifted the entire tone of the conversation, from academic curiosity to something considerably more charged. During a follow-up observation, James Webb captured the very first mid-infrared chemical fingerprint ever recorded from an interstellar object. Published shortly afterward in the astrophysical journal Letters, the results showed clear detections of water vapor, carbon dioxide, and notably methane, all concentrated close to the comet's core. Methane on an interstellar object. This was the first time methane had ever been directly confirmed on anything from outside our solar system. And methane is a molecule that carries some baggage, scientifically speaking. Here on Earth, methane is produced in essentially two ways, either through purely geological processes, volcanic activity, certain chemical reactions deep in rock, or through biological activity. Living organisms, microbes, produce methane as a byproduct of their metabolism, and it's one of a handful of molecules astrobiologists specifically watch for when they're searching for what are called biosignatures. Signs, not proof, but signs, that something worth investigating further might be present. To be extremely clear here, a biosignature is not evidence of life. It's a flag, a reason to look harder, not a conclusion. But it's also not nothing, and that's exactly the crack in the door that certain scientists chose to push on. Avi Loeb, the same Harvard astrophysicist who raised eyebrows years earlier over Oumuamua, was quick to highlight the methane detection as part of what he called a growing pattern of anomalies. Alongside the methane, he pointed to the comet's unusually large estimated mass and asymmetric jets of material being released from its surface, pointing both toward and away from the sun simultaneously, something not typically seen in ordinary comets. Loeb has stated publicly that while conventional natural explanations remain entirely plausible, the sheer number of unusual details, by his own count, more than a dozen separate anomalies, warrants serious consideration of alternative explanations. He's gone as far as calculating odds, arguing that if this object were simply a random icy rock formed through entirely ordinary natural processes, then the universe had been unusually generous, by a factor of roughly 100,000, in delivering something with this particular set of characteristics to us. Now, before this starts to sound like a runaway conspiracy theory, it's important to plant a flag firmly in the ground here. The overwhelming scientific consensus, backed by NASA leadership directly, is that this object is exactly what it appears to be on paper. An ancient, chemically unusual, extraordinarily old interstellar comet. Not a spacecraft, not artificial. A senior NASA official addressed the speculation head-on, stating plainly that nothing about this object indicates alien life or alien technology. On top of that, the SETI Institute, along with the Breakthrough Listen initiative, used the Allen telescope array to specifically scan for any artificial radio emissions coming from the object's location. They found nothing. No signal. No structured transmission. No evidence of technology whatsoever. Silence. So if it's not a spacecraft and there's no signal, what's actually left to talk about? This is where the story gets quieter and, honestly, more interesting than the headline ever suggested. Because the real scientific conversation happening around this object was never really about aliens flying a ship through our solar system. It was about something more fundamental. One researcher at NASA Goddard framed it this way: finding these rare isotopic signatures is fascinating on its own, but the bigger picture here is what it tells us about the possibility of prebiotic chemistry existing elsewhere in the galaxy. Prebiotic chemistry. The actual building blocks that, under the right conditions, over enough time, can eventually assemble into amino acids, into proteins, into the kind of chemistry that eventually, after billions of years, becomes something that can be called alive. And this comet was absolutely loaded with them. Researchers identified methanol, hydrogen cyanide, carbon dioxide, carbon monoxide, and water ice, all present in meaningful quantities. These are widely recognized as fundamental precursor molecules for amino acids, sugars, and the broader category of organic compounds considered essential for life as we understand it. The presence of this chemistry on an object that formed somewhere else entirely, roughly 12 billion years ago, strongly suggests that the raw ingredients for life aren't some rare cosmic accident unique to our solar system. They might be common, scattered throughout the galaxy, drifting on frozen comets like this one for billions upon billions of years, just waiting for the right star, the right planet, the right set of conditions to arrive at. And this is where Avi Loeb takes the idea one step further, past alien spacecraft entirely, into something arguably harder to simply dismiss. He proposed that if life, in some microbial form, had somehow been embedded deep within the icy interior of a comet like this, it's conceivable that it could survive the journey. Not by choice, not by design necessarily, but simply by being sealed away and shielded from radiation deep inside frozen material for the duration of the trip. He compared it, almost poetically, to a dandelion releasing its seeds into the wind, letting chance and distance decide where new life might eventually take root. Beyond purely accidental survival, he raised an even more provocative possibility: the concept of directed panspermia, the idea that life, or the seeds of life, could be deliberately placed inside an object like this and sent outward intentionally toward star systems with planets capable of supporting it. He described it in his own writing as the possibility of an interstellar gardener, seeding objects like this one on what amounts to a fertilization mission aimed at habitable worlds. Now, this idea is not new, and it's not something Loeb invented out of nowhere. Francis Crick, one of the two scientists credited with discovering the structure of DNA itself, a Nobel Prize winner, proposed a version of this same concept decades ago. The underlying logic is simple. Once life exists anywhere in the universe, it doesn't necessarily stay contained to its point of origin. It finds vehicles. It hitches rides. And objects moving through the galaxy at regular intervals, comets exactly like this one, could theoretically be exactly that kind of vehicle. Loeb pointed specifically to Webb's methane detection, alongside the object's unusual ratios of carbon dioxide to water and methane to water, as data points worth taking seriously in that context. He posed the question publicly, directly, without much hedging. Is it indicative that there are microbes inside this iceberg? That is not a question you'd expect to hear from a Harvard astrophysicist, referencing peer-reviewed James Webb Space Telescope data, on record, in the middle of 2026. And yet, here we are. By the time you're hearing all of this, the object itself is already gone. After making its closest approach to Earth on December 19, 2025, it continued outward, crossing beyond Jupiter's orbit by March of 2026. Current trajectory models suggest that by the early 2030s, it will have completely exited the planetary region of our solar system, continuing on into interstellar space, just as silently and just as alone as it arrived. And it is never coming back. 12 billion years of travel through the galaxy, carrying its ancient chemistry, its heavy water, its unusual carbon signatures dating back to the early universe, and its methane, from a source we still cannot fully and confidently explain, passed briefly through our small corner of the cosmos, close enough to Venus, close enough to Mars, close enough to Earth for us to actually see it clearly, and then simply left. Nobody stopped it, because nobody could. We don't currently possess the technology to launch a spacecraft fast enough to intercept an object moving at that speed with any meaningful advance warning. At some point in the deep, distant past, a gravitational interaction with a massive planet in a star system we will genuinely never identify flung this object outward with enough force that it has been drifting through the Milky Way ever since, for somewhere between 10 and 12 billion years, wandering alone. Cold, silent. And out of all that unimaginable stretch of time, all those billions of years spent crossing the empty space between stars, this brief pass through our solar system was the closest this object had come to any star since the moment it was cast out of its home system in the first place. Our sun was the warmth that finally melted its ancient surface ice, just enough, just long enough, to let us see inside it for a few brief months. And what we found inside was chemistry our own solar system simply doesn't produce. Chemistry older than almost anything we've ever directly measured. Chemistry that, in at least one specific case, methane, carries a genuine unresolved ambiguity that scientists have not yet closed the book on. We may never know exactly which star system originally launched this object into interstellar space. That information is, quite literally, unreachable. But the chemical fingerprints it carried across billions of years and delivered directly into the instruments of our best telescopes have already told us something remarkable, whether or not the more dramatic theories turn out to hold up. Parts of our galaxy were building icy bodies loaded with the raw ingredients for life, long, long before our solar system ever existed. And some of those ancient objects are apparently still out there, still drifting, still passing through star systems just like ours, largely unnoticed. That's the detail that tends to stick with people longer than the alien spacecraft headlines ever do. Not the more sensational theories, not the ongoing debate around Avi Loeb's more provocative claims, not even the methane question itself, as genuinely unresolved and fascinating as it remains. What actually stays with you is the scale of the timeline involved. Every human being who has ever lived. Every language ever spoken, every civilization that rose and eventually fell, every scientific breakthrough, every song ever written, every war fought, every single ordinary human life lived from birth to death, all of it happened inside a window of time so thin compared to the age of this single object that it barely registers as a blip. This comet was already ancient before the very stars that would one day form the material for our own sun had even finished collapsing into existence. It has seen more of this galaxy than we will ever be capable of directly witnessing ourselves. It was forged under conditions we can only approximate through models and simulations, and it passed through our tiny corner of an unimaginably large universe, warmed up just enough to briefly speak to us in the language of chemistry, gave our instruments a few short months to listen closely, and then went completely silent again, heading back out into the dark. So what did it actually tell us in the end? That the galaxy appears to be full of extremely ancient chemistry. That the fundamental molecular building blocks associated with life, or at the very least, the precursors to life, don't seem to be some incredibly rare cosmic accident confined to our own solar system. That these molecules travel. That they've likely been traveling aboard frozen messengers exactly like this one since long, long before our own sun ever ignited. That the very specific set of conditions that allowed life to eventually take hold here on Earth might not be nearly as rare or as special as we once assumed, or, depending entirely on how you choose to interpret the same set of data, it might mean the exact opposite, that our specific combination of circumstances remains far more unusual and far more precious than we've dared to hope. The data itself genuinely supports both readings, and that particular debate is almost certainly going to continue for years, possibly decades, as scientists continue analyzing the enormous volume of observational data collected during this brief flyby. But as far as the object itself is concerned, it's finished talking. It passed through our solar system, it warmed briefly under the light of our star. It shed ancient ice that had never before been touched by starlight in 12 billion years. It was measured, photographed, and analyzed by essentially every major instrument humanity currently has pointed at the sky. And now it has returned to the dark, continuing on a path that will carry it beyond anything we can meaningfully track, for the rest of time. Here's the part that should genuinely unsettle you a little, the part that rarely makes it into the headlines. This almost certainly is not a rare event. Researchers involved in the Hubble nucleus study have estimated that, statistically, there's likely to be at least one object of comparable size to this one, within a relatively close distance of the Sun at essentially any given moment in time. Scientists strongly suspect that comparably large, comparably bright interstellar objects have quietly passed through our inner solar system before on multiple occasions without ever being detected at all. We simply didn't have the right equipment pointed in the right direction at the right moment to catch them. We are, in all likelihood, constantly surrounded by interstellar travelers just like this one, most of them passing through completely unnoticed, unrecorded, and unexplained. This particular one only became visible to us because a telescope built specifically to hunt for potentially hazardous asteroids happened to catch a faint smear of light on an otherwise unremarkable night, while doing precisely the job it was originally designed to do. It ended up finding something far older, far stranger, and arguably far more important than any asteroid ever could be. It found what amounts to a message in a bottle, 12 billion years old, launched from a star system we will genuinely never be able to identify. carrying chemistry that we are still working to fully understand, and quietly posing a question that we currently do not have the instruments in place to definitively answer. Are we alone in this galaxy? Or did the beginning of an answer to that exact question just fly past us at 221,000 kilometers an hour while we were still building the tools we would have needed to truly find out? Think about what that actually means for the next time you look up at a clear night sky. Somewhere out there, right now, tonight, there could be another one of these ancient travelers already inbound, already falling toward us on a trajectory nobody has calculated yet, carrying its own frozen chemistry from some other corner of the galaxy, from some other era entirely. We got lucky with this one. A telescope built for an entirely different purpose happened to be pointed in the right direction on the right night and caught a faint smear of light before it slipped past us unseen, the way researchers now believe similar objects almost certainly have more than once throughout human history. Every time one of these things arrives, we get a few short months, sometimes less, to point every instrument we have at it before it's gone for good. No second attempt, no follow-up sample return mission. Just a narrow, unrepeatable window and whatever we manage to learn inside it. That is genuinely the position we're in as a species right now. Watching, cataloging, measuring, and hoping the next one gives us just a little more time. And maybe, eventually, the right technology already waiting and ready to actually chase one down instead of simply watching it pass us by. For now, all we're left with is the data, and a very, very long wait for the next one,